Hello and welcome back to the lecture on applied econometrics, and we have been talking about heteroscedasticity. Now, in the previous lecture, we have introduced the concept and we have shown how graphically it looks like and what are the situations it may arise. Now, in this lecture, we are actually going to see when we have data in our hand, how do we understand if that data set really has a problem of heteroscedasticity. And for that, we need to sort of understand these two kind of plots that we are going to talk about. One is residual versus fitted plot, and another is residual versus predictor plot. So, what is residual versus fitted plot? So, we have already seen that we can actually identify the presence of heteroscedasticity by plotting y hat and error. Okay. So, the error term that you already have and the predicted y hat basically. So, that is what is essentially residual versus fitted. Fitted is nothing but the fitted y. Now, or once you actually conduct the regression, you perform the regression, you get the residual versus fitted plot. And residual versus predictor is that once you actually conduct the regression, once you already have the residual, basically you get the residual after you conduct the regression. So, whatever is left out as a residual, that is what you actually take and plot it. And in this case, in the second case, you get the residual and you plot it with the x variable. So, whatever x variable is your concern, you may think that in your regression equation, it is like one particular x variable is actually influencing the error term. So, if you plot these two, then what you will get is you get a sort of plot where it will show if there is any relationship. It is basically simply looking at like a scatter plot. In a scatter plot, you simply see if you see some sort of association between the two variables. It is as simple as that. So, let us first try to actually run a regression line and a regression equation, and then we will see how the residual versus fitted is looking like, or how the residual versus predictor plot is looking like. So, we will just go back to our data set that we have been using over the time. So, this is basically national sample survey data, and in this national sample survey data I have already defined all these variables, so I am not going to define it again. I will just run the regression line and let us see if the regression is running fine. Yeah, the regression is running fine. Now, in this regression, it is a good model, reasonably good model with R square 0.38. Now, in this model, I want to see if there is any, what we can see if I do a residual versus fitted plot. So, this is residual versus fitted plot. The command is very simple in Stata, RVF, residual versus fitted, R for residual versus fitted. And if I do RVF plot, let us see what we get here. Okay, so it is basically giving us like a scatter diagram between your residual and the y hat. Okay, and if we do that, this is what you get. And you see that in this case, what we see is with the increasing value of y, fitted y, your residual is actually also increasing. So, this is something we have seen as the usual case of heteroscedasticity, where with the increasing value of x or increasing value of y, your error term is also increasing. Okay, so this is one example what we see as probably in our data set we actually have the problem of heteroscedasticity. You can use this command of y line. So, what you will get is basically you will get the 0 line. It will give a prominent sort of the 0 line where the 0 line is there. Okay. Now, the other plot is RVP plot. Now, RVP plot is nothing but the residual versus ঠিক আছে দাঁড়া একটু ঠিক আছে, no problem. I am ready. The other plot that we spoke about is the RVP plot. Now, RVP plot is nothing but the residual versus predictor plot. Now, predictor means basically your x variable. So, in this case, you note that if your model has like 3 x variables, you can actually plot your residual with all these 3 x variables. Okay, so you have to decide, you have to sort of make a sense of which variable might have some relationship with the error term, or you can actually plot all the different possibilities, like all the error terms with the different predictors. Okay, so let us actually do that. And here residual RVP, residual versus predictor plot, and I am assuming that, well, general education might have something to do with the heteroscedasticity problem. So let's just try to run it, and I see my idea was correct. So we actually see that with different levels of general education. So these are like, these are levels of education. So like class 4, class 6, class 8, and different ways NSS actually collects data. Graduation, at graduation level is probably the highest, the dispersion is very high, and probably after that it is post graduation. So as you increase the education, the dispersion is also increasing. Okay, so that is something we have to sort of we can kind of say that, well, there is a problem that the y variable is, this particular x variable might have something to do with the heteroscedasticity problem. You can also do for other continuous variables or other numerical variable like experience. Let's say if I do with experience the number of years, so it is something also making sense. It is of course not strictly diverging. It might have some bell-shaped sort of nature, and that is actually how the experience influences the wage. It actually, as your experience increases till a certain age, maybe 50, 55, 60, you actually keep on earning more, but then after a certain age, even if your experience is increasing, as per our definition of experience, you may not be earning that much. Your income is actually decreasing, right? So that actually makes sense. So essentially it shows that the error term is actually correlated with the experience, and that is not absolutely a random. So there is a correlation. It's not absolutely random. Okay, you can also plot with experience square, and let's say if we plot with the dummy variable. So here sex or gender is basically, we have two values 0 and 1, male and female, and for sector also this is basically for rural and urban. So we can expect that for females, so since they might not have a lot of opportunities, or they're so the dispersion or the observations are less in number, so the dispersion might be low. Okay, and exactly that is what we see here. So for males the dispersion is very high, but whereas for females the dispersion is actually low. And you can you can just pause the video for a moment and think what will happen if I plot for rural and urban. And if I plot it, we will see that for urban, because the opportunity is a different type, there are like the chances of getting into different occupations are like plenty. So you are likely to have more dispersion in the urban area, whereas for rural area, since the opportunities are limited, the dispersion is also going to be low. And that is exactly what we see. So in our data set, 1 is the rural and 2 is the urban, and you see the dispersion in urban area is much higher than the dispersion in the rural area. Okay, so this is the beauty of RVP plot. Now, I can ask a question that, well, we have seen in all the cases the heteroscedasticity looks like our case 1, where we said that, this our case 1, where we said that usually the error term would show a sort of a diverging nature. Okay. But will it always be the case? And that is what we are going to see now. And I'll claim that it will mostly depend on how you, how you do your, or how you specify your regression equation, how the functions are, how, what are the variables. So that is where the nature of the heteroscedasticity gets determined. So let's say I create, instead of general education, I create an idiosyncratic variable, I call it IDO, equal to 1 by general education. So whatever is the value of general education, it will be now 1 by that. And then I create another variable IDO1, and that is 1 by experience. And now if I run my regression with IDO and IDO1, let me actually do that. So I already have generated, so I will not run it again, instead I will give me an error. So if I run it with IDO and IDO1, just these two variables, let's see what we are going to get. So my regression has run fine. Now make a guess, if I plot the RVA plot and if I plot the RVP plot, where exactly the differences will be actually visible. Okay, so will it be any different if I do the RVA plot? You can pause for a moment and think about it. actually there will be no difference, because in RVA plot you are plotting the fitted y with the error term. Okay, so there might be a little bit of change in the fitted value, but the nature of the curve is going to remain same, because the y, you didn't change any functional form of the y remains y. You didn't do it log y, or you didn't do 1 by y. Okay, so if I do the RVA plot, we'll see, we'll get the same sort of residual and fitted value relationship. Okay, but if I do a RVP plot, because your explanatory variables have changed, okay, the functional form has changed, you will see the relationship to be a little different. So you see the dispersion is actually higher when your values are actually lower. Okay, and it is actually lower when your value is higher, and that is totally reasonable, because you have done 1 by general education instead of general education, right? And similarly for experience, you will also see the same thing. Okay, so you will have the highest level of dispersion at the value of 0. I mean, when like 0 or close to 0, because again here your experience, the new variable IDO1 is nothing but 1 by experience, right? So as your experience value is increasing, your 1 by experience is actually decreasing. So it is essentially showing the same thing, but this is how, just by changing the functional nature, you can actually have different types of heteroscedasticity plotted. Okay, now if I suppose do like I change the y variable. Now my y variable, instead of log wage, I sort of create a variable inverse of wage. Okay, INV wage is nothing but 1 by wage, my dependent variable is wage total. So my new variable is going to be INV wage, which is 1 by wage total. Okay, so if I run the regression here with INV wage as the y variable, so I will get the result. I'll get INV wage is not found. Okay, so that means I need to define it somehow. So let me define it. Just a second. So essentially I have to run it. Now let's see, should be working fine. Yeah, so now I got the regression with my dependent variable as INV wage. Okay, so now I have to sort of I have to see what happens to the RVA plot. So what will happen to the RVA plot? Now I have changed the y variable, right? So essentially we will see something similar to what you have seen previously. Here in this case, since you have changed your y variable, your RVA plot is going to change, right? Because your y is now 1 by y. So essentially you see that. So as your fitted values are lower, your dispersion in the error term is much higher, because now your y variable is nothing but 1 by previous y variable. So that is why your dispersion is much higher when the y variable has this new y variable has a lower value. Okay, so this is how, by changing the functional form, you can actually get different sort of representation of the heteroscedasticity. Now you may also want to actually see what happens if with the RVP plot here. So of course it will, your RVP plot is not going to change, because your the x variable has remained same. Okay, also you have, if it is IDO1 it will not, but so let's see. Oh, I have actually kept IDO1, but instead if I would have kept, say, Gen Edu add experience, so essentially without changing the form of the x variable, so I will see, and then if I do a RVP plot, then I will see it will remain, it did not change. The residual now has a, again, diverging nature of, so essentially we will see that the residuals, it will show some changes because the residuals have changed, because the model is different, but it will not be like the converging error term that we have just seen previously. Okay, so that is how we need to understand if I do a residual, residual versus fitted or residual versus predictor plot, and if we use different functional forms. So with this, we'll end the lecture here, and in the next lecture, we are going to talk about why this heteroscedasticity is a problem. Okay, so we see what is heteroscedasticity. We have seen how to understand heteroscedasticity, but in the next lecture, we are going to actually talk about why it is a problem. Thank you.